Good morning, good afternoon, or good evening, depending on your time zone. Welcome to today's NET Seminar, the first in EE Times, The Future of Semiconductor series. Today's NET Seminar entitled, Probing the Mysteries of Analog Design, brought to you by EE Times and sponsored by Linear Technology Corporation. I'm John Doubleday. Before we begin today, we've got just a few announcements. This NET Seminar is designed to be interactive between you and the panelists. Later in the program, we will ask for the most important part, your feedback. We certainly hope that you'll give it to us. If you'd like to participate in the Q&A session, click the Ask a Question link on the browser interface. Fairly self-explanatory there. We do encourage you to ask questions at any time during the presentation by typing your question into the text area of the pop-up window and simply pressing the Submit button. You may enlarge the slide window at any time by clicking on the Enlarge Slide button. This larger view of the presentation will advance automatically throughout the course of the event. And finally, if you are experiencing any problems with the video stream, such as buffering or intermittent video, just select the Preferences link below and choose a slower video speed. Now on to today's seminar. Leading today's discussion on the state of the art in analog design is Girish Matre, technology marketing consultant and former editorial director and publisher of the EE Times. Joining Mr. Matre are noted design gurus Robert Dobkin, founder and chief technical officer of Linear Technology Corporation, and Jim Williams, staff scientist, also of Linear Technology. To begin today's event, I will turn it over to Girish Matre. Girish?
Thank you, John. Let me jump right in. Probing the Mysteries of Analog Design. That's a provocative title. Is it mysterious, Bob Dobkin? Why is analog considered so mysterious? Is it fundamentally different from digital design?
It's fundamentally different, and it's a lot older technology. It goes back well before we had a lot of digital design. But analog design deals with all the states in the middle of on and off. And as such, you can have many ways of getting to your answer when you do an analog design. So it takes a lot of experience to do analog design. It takes a lot of background to do it.
So what does it take to be a good analog designer? Jim, what do you think?
I think first and foremost, it takes a willingness, a readiness, and even an eagerness to deal with ambiguity. Like Bob said, there's 100 different ways the problem may present itself. There may be 100 different ways that suggest a solution. So first and foremost, you have to be used to the idea that there is no one fundamental answer. There's a spectrum of answers, many of which may be appropriate. You have to be able to deal with ambiguity.
Go ahead, Bob.
Yeah, I think being a good analog designer is kind of like learning a language. And when you're in college, you learn all the pieces of the language. You learn the equations, you learn what the components do. And until you really know the language, you can't start putting them together. As you learn a language, one of the first things you do is you start translating other pieces of the language, and you'll see words in a foreign language, and you'll start looking them up in the dictionary, and bit by bit, you'll understand what's going on. Analog design is kind of like that. Until you've got all the vocabulary memorized, or all the subcircuits, or all the pieces put together, you're not going to be able to do your own. You'll be able to translate the ones that have been done before, but you're not going to start writing any great literature until you've got all the pieces as your own.
I understand. I wonder if it's too far out to say that it's more of an art than a science as compared to digital, or is that stretching it too much?
It's both. There's an art to it in terms of being able to follow your nose in a kind of push and prod approach, and a gut feeling for which way to go, a style, if you will. And it's my observation that many analog designers design with their own sense of style. You can absolutely identify that this circuit was done by this guy or this circuit was done by this guy because of the way they pursue the problem. But there is a very scientific and engineering, there is a very fundamental scientific and engineering foundation to all the decisions you're making. If you approach the problem as a pure artist, you're not going to build a working circuit.
Correct, yeah. It simply requires control of more operating characteristics, presumably, than digital does. Is that another way of looking at it? Does that make digital design easier, or am I being too provocative?
I don't know whether, since I'm not a really good digital designer, I can't say whether it's easier, but I do know from what I've seen, there are good digital designers, and there are great digital designers, and there's mediocre digital designers. And there's also computer programs that are digital designers. There's no computer programs that are analog designers. And each piece of an analog circuit is a trade-off, and you have to make lots and lots of trade-offs, and that's part of the art of it. Knowing where to make those trade-offs and end up with something that really functions well.
So what does it take to be a good analog designer? You know, it sounds like there's a lot of experience involved, but please expound on that, Jim or Bob.
You're going to have to be, first and foremost, grounded in some basics, which we've talked about. And also, you're going to have to be aware of the fact that analog design is fundamentally defined by parasitics. It's defined by your ability to predict when the parasitics are going to be there. It's defined by your ability to deal and negotiate with the parasitics. And it's also defined by your ability, in some cases, to utilize the parasitics within your design to make it better. They're not always bad. So there's this sense of balance that comes into play in terms of how much of basic rote book knowledge is required to solve a problem, and it is in many cases, and how much of a judgment call is required, steering a little bit outside the box, if you will, bending the rules, just how far you can bend the rules and get away with it before they snap. There's a sense of balance that's required and a sense of self-knowledge in terms of knowing what you think you can get away with and what you can't.
So most of it you learn on the job? Is that what, by doing and making mistakes? Or?
There is no substitute for bench experience with analog design problems.
I look at it a little bit differently than Jim because most of my experience has been designing the IC, not using the IC. Most of the people who are watching this are probably users of ICs, and they're working with the finished IC. So I'm looking at it from the transistor level, and Jim looks at it from the system level. But I think common in both of those is experience, knowing what not to do, what got you into trouble before, and being able to answer the right question. When something doesn't work, if you can't answer the right question and figure out what's going wrong, then you're not going to be able to fix it.
Is there a big difference between analog design at the IC level and analog design at the board level, at the system level, or do the same kinds of concerns and parameters carry over?
The board level designer has a tremendous advantage in that it's very easy and relatively inexpensive to try things out. You have a lot of flexibility when you're on a circuit board. It's very easy to make changes in real time and see what happens. That's a huge advantage when you're designing board level circuits. Changes are rapid, they're cheap, and they're easy. But the IC guy
has got to guess right pretty much the first time. You don't like to have the IC go round and round. Each time you have to change the IC, it's a 6 to 9 month process. The other thing is that as an IC designer, you have to design over a pretty wide range. You have to design typically to operate minus 50 to 150 degrees C. You better know how the transistors and the resistors change over temperature. You have to be able to handle lots of problems such as ESD, highly sensitive junctions, know how to test it at high speed, things that you don't run into as a system level designer. But the approaches are still the same. Synthesize a circuit, put it together, test it to see if it works. You test it in SPICE if you're an analog designer. I know Mr. Pease doesn't believe in that, but we're younger than he is. Then
yeah, we're kids.
I guess this is an industry joke, so we'll let that pass. Go ahead.
You test it, you figure out what's wrong, and you put it together, and then You turn it into an IC and then make it in silicon and check it out and see if it works like you expected.
Do you breadboard something before turning it into an IC, or just work on the computer, use SPICE and model it?
When I started, we breadboarded it. SPICE and models are good enough now that you can get better results by running the circuit in SPICE, especially if you're running a really fast circuit and it's running over a fast enough time period where the parasitics on a breadboard would not give you accurate results.
Yes, and so that leads me to another question, which is analog EDA, and analog EDA seems to be, in my opinion at least, a generation or two behind digital EDA in terms of its capability of automation. Correct me if I'm wrong, or expound on that if you would.
At the board level, I can see two reasons. One reason is basically a business reason. It's a smaller business for those people in the EDA world to go after. So right there you have a potential problem. But on a technical level, as I said before, analog design is defined almost entirely in terms of parasitics and how you manage them and how you deal with them. And those parasitics are very, very hard to quantify and even qualify. And as a result, it's very difficult to deal with on an EDA basis.
I would like to be able to buy EDA tools that would speed up my analog design. Right now I can simulate from a schematic. That's pretty good. I can't simulate really well from the chip yet. It's a really big job to be able to extract the chip back to a circuit that I can simulate, and most of the simulators won't handle the large number of parasitics that comes out. But analog has too many variables in it that to be able to synthesize a circuit. You can analyze it, but you can't synthesize it yet.
Let me just change the direction of the discussion a little bit. EE Times just finished a very special issue called The Future of Semiconductors. Naturally, part of the discussion was about Moore's law and the ever-decreasing line widths and feature sizes of digital circuits. Analog does not seem to have that pressure in the sense of being able to shrink a circuit dimension down to get more capability on it, but rather is using current technology in a variety of applications. Can you talk a little bit about the difference in digital and analog in terms of the push towards the state-of-the-art in semiconductor manufacturing?
Well, with digital circuitry, you look at the push towards finer line widths because your functionality is how much you can put onto a chip. The more digital circuitry you put onto that chip, the more functional it is, the better it is. And that's more transistors in a given piece of silicon. Analog doesn't work that way. The analog circuitry doesn't multiply by making it smaller. The functionality doesn't increase by making the chip smaller. A lot of analog functions are set by the voltage it works with, the accuracy of the circuit, the noise level, the power level. So when you're working with real-world parameters, those are set by the size of the silicon and do not increase by making the line width smaller. So in some cases, analog circuits that were developed 10 or 20 years ago are as good as they will get for that function. We won't see better analog circuits that do those kinds of functions in a much smaller die size because the die size is set by the functionality and the way the circuit's working.
So is it fair to say that the price functionality curve that is a cost functionality curve that is fundamental to Moore's law does not apply to analog? Historically has not applied?
It historically has not applied to analog because the chips do not get smaller. But
do they get cheaper?
The only,
by function,
the only reason analog chips get cheaper as time goes on is because maybe the wafers got bigger, the cost might have gone down a little bit, but mainly the manufacturer of those chips is willing to sell it for less. It doesn't have significant cost decreases in the manufacturability of the chip. So where in a digital circuit, as you can put more transistors on the chip, as the line width gets smaller, and that function becomes cheaper, that doesn't happen with analog.
But surely in analog, and perhaps this is limited to data conversion devices, where finer line widths and newer technologies, more advanced technologies do add to performance. Is that not fair?
That's fair. There are areas where the finer line widths have added to the performance, and that's the area of speed, because the finer line widths are inherently faster, so the devices made with those finer line widths have more functionality in terms of more data operations per second. They operate at higher speed. Data converters, data interface circuits, even RF circuits, those circuits benefit by the finer line widths, but the functionality is not significantly changing as line widths change. Once you've got a line width that will do your function, making that line width smaller doesn't necessarily do that function a lot better.
I see. You know, the other big trend in the industry, surely more debate about this on the digital side, is the system-on-chip approach, whether everything should be on one chip or whether there should be stacked die or whether there should be system in a package. What is your perspective from the analog side of the business in terms of the system-on-chip approach and or system-in-package approach? Jim?
Both of us will have answers to that.
Well, interestingly enough, hopefully they'll agree. Interestingly enough, my initial response to that is a non-technical response. And one of the things I see as making system on a chip difficult is a non-technical issue, and that's the issue of time. With today's product life cycles, 6 months, a year, you don't have a lot of time to get your product out. If you bet the farm on a large-scale system-on-chip program and it doesn't work out, you have nothing. Even if you can get the thing to work the way it's supposed to work on time, and your customer hasn't changed their mind 3 times during the development, you've got to get a test system up and running to test this thing. So there are real business issues in the way of SOC, independent of the monster technical issue of, should you put the same 2 things on a chip and try and get them to work at all? Bob?
There's some things that don't want to be on the same chip, and it doesn't make any sense to put it there. It really comes down to economics. You've got a process that'll do very fine line, high density digital, and it's got 7 layers of metal, and it's very expensive silicon. You don't necessarily want to put a big, easy to make power transistor and use up half your die just so that everything can be on one die. It's a bad economic decision. So I kind of look at the problem as a whole and say, what's the best, most efficient way of solving this problem? If it is all one chip, then that's the way to go. And part of those economics is speed to market. The other part is, do all these functions fit on the same chip? And if all those answers are yes, you go put it on the same chip. If not, you look at partitioning it so it works best.
I see. To shift gears once again and talk a little bit more about the marketplace opportunities for analog, as well as the analog contribution to state-of-the-art systems. We are in the world where handheld, portable, mobile communications and other kinds of systems are getting more mobile. How is analog enabling that? How is analog leading that, perhaps? Or how is analog contributing to that whole mobility revolution, if you would?
One of the areas that the analog has made a big change in that mobility is the areas of power conditioning and power conversion. All these mobile devices want to get maximum battery life, and that requires power systems to condition the battery power at the highest possible efficiency, and the ability to run over a wide range from full output power, whatever it is, down to memory keep-alive power. Analog ICs that are out in the last 5 to 10 years routinely get better than 95% efficiency. Can do the battery charging, can do a lot of smart functions on the chip, as well as handling the power levels, and extend the battery life for a lot of these pieces of equipment.
Is that a big is that where there's going to be a resurgence of analog in terms of the business of analog, or is how big an opportunity is it?
It's already happened. I mean, it's happened and it's been happening, and it will continue to happen as people cram more and more stuff into smaller and smaller packages and demand, among other things, greater life and higher performance in whatever functions they want in there. The analog people are just going to have to maintain pace, but it's already happened.
These smaller devices that have high functionality, the power subsystems are very complicated with backup power, ability to charge batteries. The system inside, whether it's a camera or PDA, may have 5 or 6 different regulated voltage levels inside, all off the same battery, both above the battery and below it. And they may have to condition the power as the battery changes through the output level. You may have a lithium battery that goes from 4.2 to 2.5 and need 3.3 in the middle. That's a complicated power conditioning problem to do at 95%.
And you're doing it, and you're doing that power conditioning with switching techniques in a very tight layout. So you've got all kinds of noise and radiation management issues you've got to deal with to prevent them from corrupting the operating features of the device.
And these are problems that are common to any handheld system now. There's analog circuitry that's going into the RF end, into the measurement end. There's A to D and D to A converters, line drivers for getting the data in and out, wireless systems. There's a large amount of analog in there, and it's been there right from the beginning, and it'll continue to be there.
In that vein, I wanted to ask you, in general terms, analog is the interface to the real world, and the trend in the last, I don't know, 20 years has been that you interface analog to the real world, convert it quickly to digital, and do increasing processing in the digital domain. Is that veneer of or interface to the analog world, is that thinning out, or is it thickening out? Is analog functionality taking on more, or is digital encroaching on what is traditional analog functionality? I know that could provoke some interesting comments.
That's a monster of a question, but basically, so long as transducer devices, in their various degrees of freedom, temperature, pressure, flow, video, whatever, so long as those fundamental phenomena, those transducers, and what it is they're measuring remain fundamentally analog quantities in nature, there's plenty of jobs for analog circuitry to do. You know, that's outside of power conditioning and everything else. That's just the phenomenon you're dealing with, that you're trying to detect or control. So long as that remains a fundamentally analog thing in nature, an analog approach towards monitoring it or manipulating it remains a fundamentally very good way to do it.
I like to go back to an analogy that goes back probably to about when linear was starting. And people used to ask, well, isn't analog dead? Isn't everything going to be taken over by digital? And we just point out to the CD player. And they say, yeah, there's your final records have gotten replaced with a CD player. But the CD player has more analog content than any of the old tape players ever did. It's got lasers, it's got laser drivers, it's got motors, it's got motor servos, it's got power supplies, it's got audio amplifiers, and yeah, it does have a microprocessor in there and a D to A to take the digital off the CD and turn it back into analog. But people think of a CD player as basically digital, and it's not.
Yes. So you painted a rosy picture for the analog space. Are there enough analog designers around, or is it a special breed that you have to cultivate?
There aren't enough analog designers around. There haven't been enough analog designers around, and there probably won't be enough analog designers around. And one of the fundamental reasons is they're not being trained by universities. They're not being encouraged by universities. at least not at the level that they're needed in terms of numbers. And finally, analog doesn't get the limelight in the design world. So it's very hard to get people even aware of the fact that they might be interested in this, that they might get hooked. There's always these aberrants that you find, these kids who got hooked one way or another, and that's who you're really looking for. But it's a hidden secret.
Are you a self-proclaimed aberrant, Jim, or is that what you're saying?
I'm highly aberrant.
That's interesting. I mean, perhaps I used to be an analog designer 25 years ago. Maybe I should brush up my analog skills. But it depends on my next question. Do analog designers make more money than digital designers?
I don't know, and I'm sitting here next to my boss. It's a rough question.
I think there's a lot of companies now that will have several digital designers and one or two analog designers that they kind of multiplex between functions. And these analog staff scientists are pretty well paid. I think it depends on how good you are. If you're good at your job, you probably have better job security as an analog designer. But like anything, there's all kinds of levels.
Of course, of course. So what are the biggest challenges facing analog design from your perspective? You guys make ICs, and you know, you are in touch with your customers all the time. What do your customers want? What are they asking for in the next generation product, or even now?
They want circuits that work for free. That's the goal of the customer. Practically speaking, they want circuits that are very easy to apply.
Right.
They want circuits that obviate the necessity on their board-level designer's part to deal or have to consider parasitics. And the analogy I like to use is they want a rental car at midnight in a strange airport. They want to put the key in, sit down, drive it, and it'll go. They don't want to know all the stuff that's going on in that car. They want you to make their job as easy as possible because they have a checklist of 50 items, and you're one of those items, and you have to realize that when you deal with the customer. The problem that your customer has asked you to solve, or the circuit he's asked you about, is the only thing on your list dealing with that customer, but he's got 50 items on his list. So first and foremost, what they want is a working solution that's easy to implement.
The analog circuits are getting more complex. They're getting harder to use. And the average designer is not necessarily an expert in my IC. He's an expert in his system, and my analog portion is only a small part of his system. He wants to get his system up and running. He doesn't want to have to study to become an expert in my ICs. So he'd like me to make my ICs easy to apply, have sufficient support literature that he can go use the IC when he wants to. He wants to put it in a circuit and have it work like it's expected to without surprises. And he'd like to have a steady supply of it. Now, most customers would also like second sources, but second sources are something that's disappearing these days. Plug-in second sources.
And customers are okay with that?
The engineering group, probably. The buyers don't like it because they remember the days where for almost any high-performance IC, it was made by 3 or 4 companies. Those 3 or 4 companies had the same process, essentially, and they would do a pin-for-pin copy of the IC, and it would plug in, it worked the same from many vendors. But today, high-performance ICs are made on processes developed in-house by the linear IC company that's developed the product, and that IC is unique to that company. You may have functional equivalents, but you won't have a plug-in equivalent because other companies don't necessarily have the same process.
So if I hear you correctly, what you're saying is that the customer prefers to look at the IC as a black box and is not really interested in what's inside and what technology and what particular circuit techniques you've used inside the IC to achieve the performance available at the perimeter.
That's right. I mean, what I've found in the mainstream is the rental car at midnight applies. I'm not particularly interested at midnight in what's inside that car. I just want to plug and go. And the vast majority of customers I work with, that's what they want in an IC. They want to take what it's allegedly supposed to do, drop it down on the board, and no surprises. They don't really have an interest, other than perhaps once in a while an academic interest in how it does what it does. Does it meet its pin functions on their board?
I got it. Well, I guess we can go to some questions from the audience. This is maybe time. John, do you want to pick that up?
Absolutely, Girish. I will do that. We do have questions coming in, and I want to thank you guys for sending in your questions, of course, and keep doing so. Plenty to go through right now. This one from William. He asks, in the mixed signal design, what are the major technical problems that you have encountered?
Does he mean, well, you can't answer this. Does he mean mixed signal on a chip? Or if it's mixed signal on a board, it's digital signals interfering with analog processes going on the board, noise-sensitive operations, and it's also levels. Are digital levels appropriate to exercising various parts of an analog circuit?
I've seen in the mixed signal area the inability to use the right components to get some of the analog functions done because you're working in a digital process has been one of the problems. And the other, keeping the digital noise away from the analog circuitry. If your analog system is fairly simple, you can put it on in the digital system, but when it gets to be really sophisticated, it's very difficult to develop that.
All right, one now from Frank, who asks, what is a good software or SPICE model to do accurate simulation for chip design?
That's for Bob.
Okay. The models are probably the most important thing. Maybe repeat that question.
Okay. He says, what is a good software or SPICE model to do accurate simulation for chip design?
The SPICE itself is the simulator. And most of the people that have simulators offer models. Linear Technology has a free, fully functional SPICE program available on its website. It's got schematic capture, SPICE simulation, and waveform viewing, and it's as good as many, and actually better than many of the commercial SPICEs out there. And we offer a lot of chip models to do circuit development. We've developed these models around our chips. There are models out there from other companies that are functional models for their chip, plus there are transistor models for doing the simulation.
Are there any third-party programs available that you think are worthwhile recommending, perhaps, to the audience in relationship to this question?
There are, for IC design, in-house we use our own SPICE, we use P-SPICE, we use H-SPICE, but those are for transistor level design. If you're doing board design, you want a SPICE that has lots of device models with it. Some of the devices, such as some of the SPICEs like P-SPICE, have a lot of libraries that come with the SPICE. Plus there are libraries available online.
I see.
All right, one now from Ralph, who asks, what are the most common mistakes made in analog design?
At the board level, that's easy. The three most common mistakes made in board level analog circuit design are layout, layout, and layout. And what I mean by layout is what's traditionally meant by layout, which is circuit traces, ground management, ground flow management, and thermal management. We have more problems at the board level with layout-based stuff than everything else put together. And that's particularly the case at very high resolutions, very high speeds, or both.
Okay.
Not bypassing the ICs. Supply bypass capacitor is mandatory.
All right. Question now from Sam. He asks, is SPICE useful for analog design?
That's mine.
That's yours. I'll give an addendum
Okay.
when you're done.
Spice is useful for analog design. It'll be very close to a breadboard of op amps, of switching regulators, of almost any circuit you want. You just have to be sure you ask it the right questions to get the answer you want.
At the board level, it's useful, but I think it's important for the user to realize the most important circuit component is the circuit board. I'm harping on layout again. So SPICE is useful, but it must be used at the board level in conjunction with another computer, which is the breadboard. And that's what a breadboard is. It's a computer. It's a full parallel, infinite state, heuristically programmed machine. The mistake of mistakes is to try and build your circuit using one tool, whether it's SPICE, a soldering iron, or an oscilloscope. You need all of them. And any given analog circuit designer will lean a little harder on one tool than another, and that's fine. That's a matter of style. But we see lots of people who try and design board-level circuits purely in SPICE and go directly to production, and that's a recipe for disaster.
All right.
I have a question to ask, if I can jump in.
Absolutely.
What would you say, Jim, are some of the hidden traps, and make what you will of that designers should be aware of in analog design? What are the? You mentioned layout certainly, but are there two or three others that most common mistakes that people make, perhaps, or and what should people watch out for?
The single most common trap that I see, and I fall into it lots of times, is when you see something going on in your circuit that you don't understand, that is seemingly innocuous, and you don't investigate it. What that means most of the time is your house is going to be burning down in 15 minutes. You know, you're just in deep yogurt. And in that regard, all the problems that people seem to have arise from fundamentals. I mean, it sounds trite and it sounds pedantic, but ignoring Ohm's law, ignoring charge conservation, and ignoring LDI-DT will inevitably get your house burning. If you look at, for instance, layout, it's all based on parasitics. Traces have impedances, transmission lines must be terminated, things get hot, and that heat has to go somewhere. It's all asking yourself very basic questions about what is this thing doing and what does it mean to my circuit. You have to ask yourself questions every step of the way along a design, including when it seems to be working beautifully. That's the most dangerous time in a design. When it seems to be working beautifully, you have to ask yourself questions and poke at the design to see how close to the edge of some cliff you are that you don't even know is there.
When something doesn't make sense, you need to get to the bottom of it. I remember cases where people say your comparator has really low gain. It takes a half a volt to make the output switch from low to high, and that comparator has a gain of 100,000. Well, they're looking at the output with a DVM and not a scope, and as they vary the input, the output is oscillating. So what their conclusion was that it has low gain is absolutely incorrect, because they're not asking the right question. Why does it not change like it's supposed to? And IC manufacturers are very careful to make sure that the specs on their data sheets are accurate. So when the IC doesn't perform as it's supposed to, it's important to look at all pieces of the circuit before you just blame the IC.
Let me ask a simple-minded question that harks back to the beginning of this discussion of the difference between digital and analog design, and that is that digital has two states and analog has a variety of states and varies continuously. And Jim said something about pushing the limit of, I'm paraphrasing what you said, of your design to understand all the different conditions. Talk to me a little bit about that. Is there some sort of test or burn-in process that is inherently different for analog than it is for digital systems?
Well, I can tell you at the board level, the testing begins before the circuit's even designed. When I'm faced with a board level based problem, the first question I ask myself, before I'm even worried about what kind of architecture the circuit's going to take is, how am I going to verify the performance of this thing? It's essential that you have a measurement scheme planned in your mind to verify the performance of your circuit even before you worry about how's the circuit going to work. That's really fundamental. Because if you design a circuit in such a way that it's very difficult to verify its performance, it may be working and you have no way to know it.
I understand. I think the audience has more questions.
Plenty of questions coming in, Gareth. This one from Asherwad, who asks, in mixed signal ICs with digital parts operating at lower power supplies, as process shrinks and analog circuits not keeping pace with the lowering power supplies, we would see more DC to DC converters and regulators, or I guess he's asking, will we see more DC to DC converters and regulators playing a critical role in design?
I think that's already taken place. We're finding more and more systems having DC to DC spot regulators, either linear or switching, to power these lower voltage digital circuitry. And we're seeing more and more voltages. We're seeing 1 volt, 1.2, 1.5, 1.8, 2.5, 3.3, all in the same system.
All right, we've got one coming in now from Gonzalo, this one being directed toward Jim. What is expected on an analog field applications engineer to support the analog designer in the field? And he says, thanks for your great work.
I like the guy and I like his question. What's expected from an analog field applications engineer, in my view, is almost impossible. You have to walk, I've never done the job and I'm not sure that I could. You have to walk into a strange circuit with a person you may have never met before in a laboratory you've never worked in before, and you have to either make a cogent suggestion for a way to solve a problem, or you have to take something that is already there that's non-functioning that you've never looked at before and try and figure out what's wrong with it. So first and foremost, you've got to be heads up and on your toes technically, and I think politically, because many of these situations these people walk into are